Welcome to Physics by Night. Tonight, we begin with a word you've probably heard many times before. Light year. It sounds simple. It sounds almost familiar. You may have heard scientists say that a star is 4 light years away, or that a galaxy is millions of light years from Earth. And because the word has year inside it, it almost feels like time. But a light year is not a measure of time. It is a measure of distance. And not just any distance. It is the distance light travels in 1 full year, moving at the fastest speed the universe allows. When you truly begin to understand what that means, the night sky changes. The stars stop being simple points of light. They become messages from the past. Some of them left their stars years ago, some centuries ago, some before anyone you know was even alive. And suddenly space does not feel empty anymore. It feels deep. It feels delayed. It feels almost impossible for the human mind to hold. So settle in. Let the room grow quiet. We will move slowly tonight, one scale at a time, from the distances your mind already understands to the distances that make the universe feel almost unreal. And before we go farther, if this kind of calm physics journey helps you relax, a quiet like or subscribe helps the channel grow. You can also leave a comment telling me where you're listening from tonight and what time it is there. Now, before we can understand a light year, we have to begin with something much smaller, the distances our minds were actually built to understand. There is a reason ordinary distances feel real to us. A mile down the road, a few blocks to the store, a short drive across town. These are not just numbers, they are experiences. They have weight in the mind because we can attach them to memory. We know what it feels like to walk them, to drive them, to wait through them, to pass the same traffic light or gas station or quiet neighbourhood corner along the way. If someone tells you a grocery store is 5 kilometres away, you do not need a calculator to understand it. You may not picture the exact number, but you can feel the journey. Maybe it is a few minutes by car. Maybe it is a longer walk than you would want to take on a hot afternoon. Maybe it is close enough to feel local, but far enough that you would still grab your keys. That is the kind of distance the human brain understands. 1 kilometre is not abstract. At a normal walking pace, it might take about 10 or 12 minutes. You can imagine that. You can place yourself inside it. You can picture shoes on pavement, a few turns down familiar streets, perhaps the slow change from one block to the next. It is a distance that still belongs to the body. Even larger distances can remain understandable if they fit into human routines. A city 200 kilometers away may sound far, but it is still something you can plan. You can imagine a morning drive, a highway, a stop for coffee, a few hours of passing fields, signs, towns, bridges and exits. You know that if you leave early enough, you can arrive before lunch or sometime in the afternoon. The distance has become large, but it has not become impossible. Even the journey across an entire country can still feel, in some way, human. New York to Los Angeles is roughly 4,500 kilometers. That is a very long way, but people make that trip all the time. A plane can cross it in several hours. A road trip can turn it into days of changing landscapes, city streets, open highways, plains, mountains, desert, then the far edge of the Pacific. It is huge, but it still has a story. It still has a beginning and an end. You can imagine someone making the trip, watching the world change outside the window. The Earth itself pushes this feeling further. The circumference of our planet at the equator is a little over 40,000 kilometers. That number is large. It is far beyond any ordinary walk or drive. And yet, even this can still be held in the mind because we know people have crossed oceans, circled the globe, flown from continent to continent, and mapped the surface of the world. The Earth is enormous from where we stand, but it is not incomprehensible. It is a place. It has maps, It has coastlines. It has countries and routes and time zones. You can imagine travelling around it slowly, patiently, one segment at a time. This is the scale our brains were made for. Not because the brain was designed to understand the universe, but because it was shaped by survival. For most of human history, distance meant practical things. How far to the next source of water? How far to shelter? How far to the edge of the forest? How long before sunset? How much energy it would take to return home? A distance was not just a measurement. It was a question of effort, safety, memory, and direction. That is why everyday distance feels solid. It is tied to the senses. We know the feeling of a long walk. We know the boredom of a long drive. We know the relief of finally arriving. The body gives the number meaning. But astronomy quietly removes the body from the equation. Once we begin speaking about millions of kilometers, then billions, then trillions, something changes. The number may still be correct. It may still be written neatly on a page. But it no longer creates a picture inside the mind. It becomes too large to walk, too large to drive, too large to cross with any human rhythm. At that point, distance stops feeling like a road. It becomes emptiness. And this is where space begins to do something strange to human intuition. The same measurement system that works perfectly for towns, countries, and even the Earth itself begins to feel thin and fragile. Kilometers are still accurate. They still tell the truth, but emotionally they stop helping. The first real crack in that familiar sense of distance appears when we leave Earth behind and look toward the closest world in the sky. The first place where ordinary distance begins to fail is not some faraway star. It is the moon. The same moon you can see from a backyard, a city balcony, a bedroom window, or a quiet road late at night. It looks close because it belongs to our sky. It rises and sets with familiar patience. It has been above every human generation, every ancient village, every ocean crossing, every night where someone looked up and felt less alone. And because we can see it so easily, the moon almost feels nearby, but it is not nearby in any normal human sense. The average distance from Earth to the moon is about 384,000 kilometers. Written down, the number is manageable. It does not look as impossible as the numbers we will meet later. 384,000. You can say it in a sentence. You can place it on a diagram. You can put it into a textbook. But feeling that distance is something else entirely. Imagine driving at highway speed, not for an hour, not for a day, not even for a week, but continuously, without stopping, without sleeping, without traffic, without weather, without the need for fuel. Even then, the journey would stretch far beyond anything that feels like ordinary travel. The moon is not a distant city. It is not another continent. It is not a place you can reach by following roads across the surface of Earth. Between here and there is no landscape, no gas stations, no mountains passing by the window, no signs telling you how many miles remain, no towns glowing in the distance. There is only the black space between worlds and a small grey sphere hanging quietly at the far end of it. This is why the Apollo missions remain so powerful in the human imagination. When astronauts travelled to the moon, they were not simply taking a long trip. They were leaving the scale our bodies understand. They were launched from Earth by enormous rockets, accelerated to speeds far beyond anything a car or airplane could approach, and still, the journey took about 3 days. 3 days, that is the strange part. At speeds that would cross countries in minutes, at speeds that make highway driving look almost motionless, it still took days to reach the nearest world in the sky. The moon is close enough to light our nights, close enough to pull gently on Earth's oceans, close enough to show its craters through a small telescope, And yet it is far enough that even the most daring human voyage required days of crossing emptiness. The moon teaches us something important before we ever speak of stars. It shows us that visibility can be misleading. Just because something is easy to see does not mean it is easy to reach. The sky compresses distance. It places the moon above us as if it were attached to the darkness, as if it were simply a lantern hanging in the night. But physics does not care how close something feels. Physics measures the gap, and the gap is enormous. If Earth were the size of a basketball, the moon would not be touching it. It would not be hovering just above its surface, the way many simple drawings make it appear. It would be several meters away, a much smaller ball sitting across the room. Most diagrams of Earth and the moon quietly lie to us, not because they mean to, but because the real scale is inconvenient. If you draw Earth and the moon at their true size and true separation, the page becomes mostly empty space. That emptiness is the point. The moon is the first lesson in how space works. Objects may appear close in the sky, but the distance between them is dominated by darkness. Earth is not surrounded by crowded worlds. It is surrounded by room. Vast, silent room. And still, the moon is only our nearest celestial neighbour. That is the part worth holding on to. This is the easy one. This is the reachable one. This is the world humans have actually visited, the one whose distance has been crossed by machines and people, the one whose surface has carried footprints. And even this distance already strains the imagination. The moon begins to loosen our trust in familiar units. Kilometres still work here, but they no longer feel natural. 384,000 kilometres is accurate, but it does not give the body anything to hold. It is too far to walk, too far to drive, too far to understand as a journey made of ordinary effort. It is a number that points away from Earth, a number that quietly tells us we've entered a different kind of scale. And if the nearest world already feels this distant, then the next step outward becomes even stranger. Because beyond the moon, beyond the orbit of Earth, sits the object that feels most immediate of all, the sun. The moon teaches us that space is wider than it looks, but the sun teaches something even stranger, because the sun feels immediate. It is not a pale object hanging quietly in the night. It is the centre of the day. It warms your skin, it brightens the room, it throws shadows across the ground, it tells your body when to wake, when to move, when the morning has arrived. Of all the objects in space, the sun feels almost personal, almost close, because every day on Earth is built around it. And yet the sun is about 150 million kilometres away. That number is difficult to hold. 150 million. You can say it. You can write it. You can put commas in the right places, but the mind does not know where to place it. It is no longer a long drive or a flight or a voyage around the world. It is not even the distance to the moon multiplied a few times in a way that still feels visual. It is a scale where kilometres begin to lose their emotional meaning. A kilometre is something the body understands. 150 million kilometres is something the body cannot translate. You cannot imagine walking it. You cannot imagine driving it. Even if you tried to picture a road stretching from Earth toward the sun, the image fails almost immediately. The road would pass beyond the moon, beyond anything familiar, and then continue through emptiness for a distance that simply refuses to become real. And this is still not a distant star. This is our own star, the star we orbit. The star whose light makes every tree, every ocean, every weather system, every harvest, every ordinary afternoon possible. The sun is so central to life on Earth that it feels like part of our environment rather than a distant object in space. But physics quietly reminds us that familiarity is not closeness. At the scale of the solar system, even the nearest source of daylight is far enough that speed itself begins to matter. Light from the sun does not arrive instantly, it travels, and even though light moves faster than anything else in the universe, it still takes about 8 minutes and 20 seconds to cross the space between the sun and Earth. That means the sunlight touching your face is already old. Not ancient, not centuries old, not the kind of old we will meet when we look at distant stars, but still delayed. Still not now. The sun you see in the sky is the sun as it was more than 8 minutes ago. The light had to leave the solar surface, cross 150 million kilometers of space, and only then arrive at Earth. This is one of those facts that seems small at first, but changes the way the universe feels. Because if something happened to the sun at this exact moment, Earth would not know right away. The information would not arrive instantly. The light carrying that change would still be on its way. For more than 8 minutes, the sky would continue showing us the old sun, the sun from moments before. The present would have happened there, but we would still be seeing the past here. That is the first quiet hint of a deeper truth. Distance and time are not as separate as they seem. In daily life, we treat them differently. Distance is how far something is. Time is how long something takes. But in space, the two begin to lean into each other. The farther away something is, the older its light becomes by the time it reaches us. The sun is the first place where this becomes visible, not because the delay is large enough to feel during the day. You do not notice the 8-minute gap when sunlight enters your window. You do not look outside and feel a delay in the sky. The world appears immediate because your senses were not built to detect light travel time across astronomical distances, but the delay is real. The sun feels present, but it is not perfectly present. It is near enough to shape every second of life on Earth, yet far enough that even light needs time to get here, and that changes the meaning of distance. A distance is no longer just empty space between two places. It is also a delay in knowledge, a delay in vision, a delay in the arrival of reality. This is where kilometers begin to feel inadequate. 150 million kilometers is accurate, but it does not explain the strange feeling of living 8 light minutes from your own star. It does not explain why the sky is not showing you the universe exactly as it is, but as light has had time to deliver it. And if the sun, our closest star, already comes to us with an 8-minute delay, then the stars beyond the sun will ask far more from the imagination. To understand why that delay matters, we have to talk about the fastest thing the universe allows. The strange thing about light is that it feels instant because our lives are small. Turn on a lamp and the room appears. Open your eyes in the morning and the world is already there. Look across the street, across a room, across a field, and light seems to arrive with no delay at all. As far as the human body can tell, seeing happens immediately. But that is only because the distances around us are tiny compared to the speed of light. Light moves at about 300,000 kilometers every second. That number is so large that it almost stops being a speed in the ordinary sense. A car on a highway might move at around 100 kilometers per hour. A commercial jet might move close to 900 kilometers per hour. Even a spacecraft traveling faster than anything humans normally experience is still slow compared with light. Light covers 300,000 kilometers in 1 second. In a single second, it could travel around Earth's equator about 7.5 times. In the time it takes to blink, light could cross distances that would take airplanes hours, cars days, and human footsteps years. It is faster than anything in ordinary life by such a wide margin that the mind has almost nothing to compare it with. And yet the important part is not only that light is fast, the important part is that light is not infinite. It has a speed. That means light takes time to go from one place to another. In a small room, that time is so tiny you could never notice it. Light from a lamp may reach your eyes in a few billionths of a second. Your brain cannot feel a delay that small, so the room seems to appear all at once. But the delay is still there. The universe is not updating instantly, it is sending information at a speed limit. Across short distances, that limit hides itself. Across astronomical distances, it becomes one of the most important facts in all of physics. The moon gives us a gentle example. It is close enough to hang in the night sky like something familiar, but light still takes about 1.3 seconds to travel from the moon to Earth. When you look at the moon, you're seeing it not quite as it is right now, but as it was a little over 1 second ago. That delay is small, but it is real, and it mattered during the Apollo missions. When astronauts on the moon spoke with mission control back on Earth, their voices travelled as radio waves, which move at the speed of light. A message from the moon took about 1.3 seconds to reach Earth. A reply from Earth took another 1.3 seconds to reach the moon, so every exchange carried a soft pause inside it. Not because someone was hesitating, because space itself was in the way. Mars makes the delay impossible to ignore. Depending on where Earth and Mars are in their orbits, a radio signal can take several minutes, or more than 20 minutes, to cross the distance. That means you cannot drive a rover on Mars the way you might drive a remote-controlled car in your yard. There is no instant steering, no quick reaction, no turning the wheel the moment you see an obstacle. Engineers have to plan commands, send them across space, wait for them to arrive, and then wait again for the rover's response to come back. A simple problem that could be corrected in seconds on Earth becomes something slower, more patient, more deliberate on Mars. The distance has turned communication into waiting. Go farther still, out towards Saturn, and the delay stretches into the scale of hours. A spacecraft near Saturn sends images back to Earth as radio signals. Those signals race through the solar system at the fastest speed possible, and still they may need more than an hour to arrive. By the time scientists receive the image, the spacecraft has already moved on. The moment they are seeing is no longer the moment that exists. This is what light speed does to the universe. It gives every distant thing a delay. For most of human history, it was natural to imagine that light was instant. You open your eyes, and there was the world. The stars appeared. The sun rose. The moon shone. Nothing in everyday experience suggested that vision needed travel time. But careful astronomy began to reveal otherwise. Observations of Jupiter's moons showed that their eclipses seemed to happen slightly earlier or later depending on Earth's position in its orbit. The difference made sense only if light needed time to cross space. That discovery changed everything. Light was not immediate. Light was fast beyond imagination but still finite. And once that idea enters the mind, the sky becomes different. The universe stops being a single present moment spread out around us. It becomes layers of arrival times. The moon is just over a second old. The sun is more than 8 minutes old. Mars may be several minutes old. Saturn may be more than an hour old. Every distance becomes a delay. Every view becomes a message that had to travel. This is why light is not just another fast thing. It is the messenger of the universe. It carries images, warmth, colour, radio signals, information, and the history of distant objects. Almost everything we know about the stars comes from light that crossed space before reaching us. And because light has a speed, astronomy is never only about where things are. It is also about when their light left. This is the quiet doorway into the idea of a light year. If light moves a certain distance in 1 second, then it moves a much larger distance in 1 minute, a larger distance still in 1 hour, and if it keeps travelling for an entire year, without slowing down, without stopping, crossing darkness at 300,000 kilometers every second, then the distance it covers becomes the unit at the centre of this journey. Now we can finally define what a light year really means. Now the word begins to make sense. A light year sounds like time because it contains the word year, and that is what makes it a little misleading at first. We hear year, and the mind naturally thinks of calendars, birthdays, seasons, one trip around the sun, a measure of time passing. But a light year is not time. A light year is distance. It is the distance that light travels in one full year. That is the entire idea. Simple on the surface, almost gentle. Light moves. A year passes. The distance light covers during that year is called 1 light year. But once you place the numbers inside that sentence, the simplicity starts to disappear. Light travels at about 300,000 kilometers every second. Not every hour, not every minute, every second. While 1 heartbeat passes, light has already crossed a distance so large it could wrap around Earth again and again. While a single breath leaves your body, light has moved farther than any machine humans have ever sent in the same tiny slice of time. So what happens when light keeps going? 1 second becomes 1 minute. 60 seconds of motion at 300,000 kilometers per second. That is already 18 million kilometers. 1 minute of light travel is larger than almost every distance our daily minds can imagine. Then 1 minute becomes 1 hour, 60 more minutes. Light keeps moving. It does not slow down. It does not pause. It does not rest between worlds. It simply continues through darkness, carrying energy, images, warmth, and information. Then 1 hour becomes 1 day. Then 1 day becomes 1 year. And after an entire year of travelling at the fastest speed the universe allows, light has crossed about 9.46 trillion kilometers. That is 1 light year. 9.46 trillion kilometers. The number is accurate, but accuracy is not the same as understanding. You can write it down. You can say it clearly. You can use it in an equation. But the mind does not easily turn that number into a picture. It is too far beyond walking, too far beyond driving, too far beyond flying, too far beyond any journey that fits inside a human life. This is where the word trillion becomes part of the problem. We hear million, billion, and trillion so often that they can begin to sound similar. They all mean very large in casual speech, but they are not similar at all. They're separated by enormous jumps. 1 million seconds is about 11.5 days. That is large, but still understandable. You can picture 11 days. You can imagine waiting that long. It is less than 2 weeks. It belongs to ordinary life. 1 billion seconds is about 32 years. Now the scale has changed. 32 years is a generation. It is childhood becoming adulthood. It is enough time for cities to change, for families to grow, for whole eras of culture to come and go. 1 billion is not just a bigger million, it is 1,000 millions, and 1 trillion seconds is about 31,700 years. That is no longer ordinary time. That reaches back before writing, before cities, before agriculture had spread across the world. It reaches into a human past of stone tools, ice age landscapes, and small bands of people moving through a world without maps, without nations, without permanent roads. That is what trillion means, and 1 light year is not 1 trillion kilometers. It is 9.46 trillion kilometers, almost 10 trillion. Now remember what a kilometer is. A kilometer is not abstract. It is a real distance, a distance you might walk in 10 or 12 minutes. A distance that could contain houses, sidewalks, trees, intersections, parked cars, small shops, and ordinary details of life. It is a stretch of the world you can understand with your feet. A light year contains 9.46 trillion of those, not symbols, not empty digits, actual kilometers, one after another, until the number becomes too large for imagination to follow. This is why astronomers needed a different unit. Kilometers work beautifully on Earth. They work for cities, highways, countries, even the distance to the moon and the sun if we're willing to accept large numbers. But when we begin measuring the distances between stars, kilometers become too small. The numbers swell until they stop helping. Using kilometers to measure the distance to stars is like using inches to measure the width of an ocean. It can be done. It is technically correct. But the number becomes so large that it no longer gives the mind a useful shape. A light year gives that distance a cleaner form. It connects space to light, and it connects distance to time. If a star is 10 light years away, its light took 10 years to reach us. If a galaxy is 2 million light years away, the light we see tonight began travelling 2 million years ago. The unit does two things at once. It tells us how far away something is, and it tells us how old the light is when it arrives. That is why the light year is so powerful. It is not just a measurement. It is a reminder that the universe does not come to us instantly. Everything distant is delayed. Everything far away is seen through travel time. The sky is not a single present moment. It is a layered collection of arrivals. Some light left moments ago, some left years ago, some left before human civilization existed, and some has been crossing space for billions of years. A light year, then, is more than a convenient astronomical unit. It is the first doorway into the true scale of the cosmos. It tells us that even the fastest thing in nature needs time. It tells us that space is not simply large, but large in a way that stretches time along with it. 1 light year is the distance light travels in a year, a simple sentence. But inside that sentence is 9.46 trillion kilometers of darkness. And even 1 light year becomes easier to feel if we climb toward it slowly. 1 light second, 1 light minute, and 1 light hour at a time. The easiest way to approach a distance this large is not to jump straight into it. A light year is too wide for the mind to hold all at once. So instead of trying to imagine the whole distance immediately, we can climb toward it slowly. 1 small step of light at a time. Begin with 1 light second. That means the distance light travels in 1 second. At about 300,000 kilometers per second, 1 light second is roughly 300,000 kilometers, and already with only 1 second of light travel, we've left human distance far behind. 300,000 kilometers is almost the distance from Earth to the Moon. Not quite all the way there, but close enough to feel strange. In 1 second, light can cross almost the same kind of distance that took Apollo astronauts several days to travel. Think about that gently. A journey that required rockets, fuel, planning, danger, courage, and days of travel is almost covered by light in a single second. 1 second. That is how wide even the smallest rung of this ladder already is. Now stretch that second into a minute. 1 light minute is 60 light seconds. Since light moves about 300,000 kilometers every second, in 1 minute it travels about 18 million kilometers. 18 million kilometers is no longer something the imagination can place inside ordinary experience. It is not a road, it is not a flight, it is not a voyage around Earth. It is a distance so large that even the Moon becomes only a nearby marker behind us. And yet, 1 light minute is still small compared with the solar system. The Sun is about 8 light minutes away from Earth. More precisely, sunlight takes about 8 minutes and 20 seconds to reach us. That means the daylight outside your window has been travelling for more than 8 minutes before it becomes part of your morning. A sunrise is not only light arriving, it is light completing a journey. That is one of the quiet lessons of the light ladder. Every step upward turns distance into waiting. 1 light second is a delay you might notice in a conversation with astronauts on the Moon. 1 light minute becomes the scale of deep space inside the solar system. 8 light minutes becomes the distance to the star that keeps Earth alive. Now climb again. 1 light hour is 60 light minutes. At the speed of light, that becomes a little over 1 billion kilometers. 1 billion kilometers. By now, the numbers have already become difficult to feel. but the solar system gives us places to attach them to. Saturn, depending on where Earth and Saturn are in their orbits, sits roughly around the scale of light hours away. When a spacecraft near Saturn sends a signal back to Earth, that signal does not arrive instantly. It crosses the black distance between worlds at the fastest speed possible, and still, the message can take more than an hour to reach us. This means an image taken near Saturn is already old when scientists receive it. The spacecraft has moved, the planet has turned, the moons have shifted along their orbits. The moment has already become the past before it reaches Earth. At light-hour distances, the universe begins to feel less like a place we watch in real time, and more like a place that sends delayed letters across darkness. Now keep climbing. 1 light day is 24 light hours. That's about 25.9 billion kilometers. This is a scale where even the fastest human-made objects begin to seem almost still. Voyager 1, launched in 1977, has been travelling outward for decades. It has crossed beyond the planets. It has passed into interstellar space. It is one of the most distant objects humanity has ever created. And yet, after nearly half a century of travel, Voyager is only on the order of a light day distance from Earth. That is astonishing. A machine built by human hands, moving faster than any airplane, faster than any car, faster than any ordinary object in human life, has spent almost 50 years travelling outward, and light covers a comparable distance in about a day. This is not because Voyager is slow. Voyager is incredibly fast by human standards. It is just that light is almost unfairly fast, and space is almost unfairly large. This is where the ladder begins to do its work. It does not make the universe small. It does not make the numbers easy, but it gives the mind a rhythm, a way to rise gradually instead of being thrown into the full scale all at once. 1 light second, nearly the moon. 1 light minute, 18 million kilometers. 8 light minutes, the sun. 1 light hour, the realm of the outer planets. 1 light day, the edge of our direct human reach where Voyager drifts through the dark. Then comes 1 light week. 7 light days. At that distance, the sun would no longer feel like the overwhelming ruler of the sky. It would still be bright, but it would begin to look more like a brilliant star among other stars. The planets would be tiny and hard to see. Earth would be invisible to the naked eye. Everything we call home would be compressed into a small region around 1 ordinary point of light. 1 light month stretches the mind even further, about 30 light days, hundreds of billions of kilometers. At that distance, the solar system becomes difficult to picture as a place of worlds. The planets, moons, asteroids and spacecraft all shrink into a small neighborhood around the sun. And still, after all of that climbing, we have not reached 1 light year. 1 light year is 365 light days. It is 12 light months. It is 52 light weeks. It is 8,760 light hours. It is 525,600 light minutes. It is over 31 million light seconds. And each one of those seconds is already close to the distance from Earth to the Moon. That is what makes the light year so difficult to feel. It is not simply large. It is built from units that are already enormous. A light second already breaks everyday distance. A light minute already leaves the moon far behind. A light hour reaches into the scale of the outer planets. A light day humbles even our fastest spacecraft. And a light year gathers all of that into 1 unit. This is why astronomers use it. Not because it makes space small, but because it makes space speakable. Without light years, the distances between stars would be buried under strings of digits too long to feel. With light years, we can at least begin to compare one distance with another. 4 light years, 10 light years, 1,000 light years, 100,000 light years. The words are simple, the meaning is not. And once we've climbed this ladder, Once we understand how much distance hides inside even 1 year of light travel, we can finally ask the question that changes the night sky. How far away is the nearest star? After climbing from light seconds to light minutes, from light hours to light days, and finally to the distance light covers in an entire year, we can ask a simple question that suddenly no longer feels simple. How far away is the nearest star? Not the sun. The sun is our own star, the one Earth circles, the one whose light fills our days. But beyond the sun, beyond the planets, beyond the edge of the solar system, there is another star that holds a special place in astronomy because it is the closest known star to us. Its name is Proxima Centauri, and even though it is the nearest star beyond the sun, it is about 4.24 light-years away. At first, that number does not sound terrifying. 4.24. It almost sounds small, smaller than 5, a number you could write easily on a page, a number that feels gentle compared with millions and billions and trillions. But that is where the light-year quietly changes the meaning of closeness. Because 4.24 light-years is not 4.24 years of waiting on a calendar. It is 4.24 times the distance light travels in a year. That means Proxima Centauri is more than 40 trillion kilometers away. 40 trillion. And this is the closest one. This is our nearest stellar neighbour. The word nearest becomes strange here. In ordinary life, nearest means easy. The nearest store, the nearest gas station, the nearest town, something close enough to reach without much planning. But in astronomy, nearest can still mean almost impossibly far. Proxima Centauri is part of the Alpha Centauri system, a small red dwarf star too dim to see with the naked eye. That detail feels almost poetic. The closest star to us, besides the Sun, cannot simply be looked at from a dark field by human eyes alone. It is nearby in cosmic terms, but hidden from ordinary sight. The sky is full of stars we can see more easily, but the closest one beyond our Sun is small, faint, quiet, and distant. If you could somehow travel toward Proxima Centauri at the speed of the fastest spacecraft humans have ever built, the journey would still take thousands of years. Not a long vacation, not a career, not a lifetime. Thousands of years. Longer than recorded history. A mission launched when the first cities were rising on Earth might still not have arrived. Generations would pass. Languages would change. Nations would appear and disappear. The people who built the spacecraft would be ancient memory before the spacecraft came close to its destination. That is what 4.24 light-years means when translated back into human travel. It means the nearest star is not simply far away. It is separated from us by a kind of distance that civilization itself has barely learned how to imagine. And this is one of the reasons light-years matter so much. They make the numbers shorter, but they do not make the universe smaller. Saying Proxima Centauri is 4.24 light-years away feels clean. It feels manageable. But inside that clean number is a gulf so large that almost every form of travel humans know becomes meaningless. We can send spacecraft across the solar system. We can land machines on Mars. We can fly past Jupiter, Saturn, Uranus, Neptune, and beyond. We can launch probes that drift into interstellar space. But reaching another star is a different kind of problem. It is not only a question of building a better rocket, it is a question of confronting the scale imposed by light itself. Chemical rockets, the kind that carried humans to the moon, are extraordinary machines, but they are not built for crossing light years. Even our fastest probes move at only a tiny fraction of light speed. To make interstellar travel feel even remotely practical, we would need something radically different. This is why ideas like Breakthrough Starshot capture the imagination. The proposal is not to send a giant spaceship, but a tiny probe, perhaps no heavier than a small chip, attached to an extremely thin reflective sail. Instead of carrying enormous fuel tanks, It would be pushed by powerful lasers from Earth, accelerated by light itself. If such a craft could reach about 20% of the speed of light, it might arrive near Proxima Centauri in roughly 20 years. That sounds almost miraculous compared with thousands of years. But even this idea is filled with enormous challenges. The lasers would have to be incredibly powerful and precisely aimed. The tiny spacecraft would have to survive traveling through space at a significant fraction of light speed. Even a small grain of dust could become dangerous at those speeds. Then, after the probe rushed through the Proxima system, it would need to send information back across more than 4 light-years of darkness. And even if everything worked perfectly, the signal returning to Earth would still take more than 4 years to arrive. So the trip would not simply be 20 years, it would be 20 years to get there, and then more than 4 additional years before we could receive the first whisper back. That is the nature of light-year distance. Even when you solve the journey, you have not solved the delay. Even when you reach across space, information still has to come home. Proxima Centauri gives us a quiet but powerful lesson. It shows that the universe is not arranged on a human scale. The stars may look close together in the night sky, sprinkled like points across a dark ceiling, but the appearance is misleading. Between one star and another lies an ocean of distance so vast that even light needs years to cross it. The nearest star is not a nearby lantern. It is an island across a black sea, and yet there is something beautiful in that. We may not be able to visit Proxima Centauri easily. We may not be able to cross that distance with anything like ordinary technology, but its light still reaches us, patiently, quietly. After years of travel, photons from that faint red star arrive here, touching our telescopes, carrying evidence that another sun exists beyond our own. We cannot reach it easily, but we can know it is there, and that is one of the strange gifts of astronomy. The universe can be unreachable and still visible, distant and still present, separated from us by years of a light travel, and yet somehow connected to us by the very light that crosses the dark. And once that idea settles in, the night sky changes again, because if even the nearest star reaches us by old light, then every star we see is not simply a place, it is also a moment from the past. There is a quiet secret hidden in every clear night sky. When you look up at the stars, you're not seeing the universe exactly as it is right now. You're seeing light that has been travelling toward you for years, decades, centuries, or sometimes far longer. Every star is not only a place in space, it is also a message from another time. This is one of the strangest consequences of the light year. The farther away something is, the older its light becomes by the time it reaches your eyes. The star may still be there. It may be almost unchanged. It may have shifted slightly, dimmed, brightened, or gone through some slow change that human eyes could never notice from so far away. But the version you see is never perfectly current. You are always seeing the past. Take Sirius, the brightest star in the night sky. Sirius is about 8.6 light-years away. That means the light from Sirius has travelled for 8.6 years before arriving here. When you look at Sirius tonight, you are seeing it as it was more than 8 years ago. That number is small compared with the distances we'll meet later, but it's already enough to make the sky feel strange. 8 years is not nothing. 8 years ago, your life may have looked different. You may have lived in a different place. You may have known different people, had different routines, different worries, different hopes. And while all of that was unfolding here on Earth, the light from Sirius was quietly crossing space, moving through the dark at the fastest speed the universe allows. Only now does it arrive. Only now does it become part of your night. Vega gives the feeling a wider shape. Vega is about 25 light-years away. If you are 25 years old, then the light you see from Vega tonight began its journey around the time you were born. If you are older than that, It left during an earlier chapter of your life. If you are younger, it began travelling before you existed at all. That is a strange thought. A photon can leave a star before you are born, cross empty space for your entire lifetime, and finally enter your eye on an ordinary night when you happen to look up. The star becomes personal, not because it knows you are here, but because its light has crossed years that your own life has lived through. Then there is Betelgeuse, the reddish star in Orion, one of the most recognizable stars in the winter sky. Betelgeuse is roughly 550 light-years away. Its light began travelling toward Earth around the time of the Renaissance. When that light started crossing space, the modern world had not yet fully taken shape. Ships were crossing oceans with uncertainty. Books were becoming easier to spread. Artists and thinkers were changing how humans saw themselves and the world. And through all of that, light from Betelgeuse was travelling, century after century, through wars, inventions, migrations, revolutions, discoveries, losses and ordinary lives that appeared and vanished on Earth. Tonight that old light reaches us. Betelgeuse is especially haunting because it is a massive star near the end of its life. Someday, astronomically speaking, it will explode as a supernova. It may not happen for thousands of years. It may not happen for far longer. But the important idea is this: if something dramatic happened there, we wouldn't know until the light arrived. Betelgeuse could change, and Earth would continue seeing the older version until the news crossed 550 light-years of space. In that sense, the sky is not a live broadcast. It is an archive, a collection of delayed arrivals. Each star is showing us a different age of the universe. Some are only a few years old by the time we see them, some are centuries old, some are thousands of years old. And when telescopes look beyond the Milky Way, some light is millions or billions of years old, carrying images from times before humans, before mammals, before even Earth looked the way it does now. The night sky is not one moment. It is many moments layered together. This is why the word light year is so powerful. It does not only measure how far away something is, it tells us how long its light has been travelling. Distance becomes time, space becomes memory. The darkness between stars becomes a kind of waiting room where light carries old information across the universe. Even the North Star, Polaris, is not truly present in the way it seems. Its light takes centuries to reach us. When people used it to navigate across oceans, they were steering by old light. When travellers looked north and found their way, they were trusting a signal that had left its star long before their own lives began. There is something deeply calming about this. Every night sky is made of patience. Nothing arrives instantly. Nothing distant is rushed. The universe sends its light across enormous stretches of darkness, and the light arrives when it arrives. A star does not need to be close to be seen. It only needs to shine long enough for its message to cross the distance. And we, standing on this small planet, receive those messages quietly. We look up, an ancient light enters the eye. The brain turns it into a point of brightness. The mind calls it a star. But what we are really seeing is a bridge between then and now, a star as it was, a photon that survived the dark, a past moment arriving gently in the present. This is what makes the sky feel deeper once you understand light years. The stars are not decorations scattered across night. They are distant suns, separated from us by enormous stretches of space and time. They are reminders that the universe is not only vast outward, but vast backward. To look far away is to look long ago, and the stars we see with our eyes are only the nearest islands of light. Beyond them, the same measure stretches across the entire galaxy. The stars we see at night are only the beginning. They feel countless when the sky is dark enough. Thousands of small points scattered above us, some bright, some barely visible, some grouped into patterns humans have named for thousands of years. But even on the clearest night, with no city lights and no clouds, your eyes are seeing only a thin local sample of what surrounds us. Most of the galaxy is hidden from ordinary sight. The Milky Way is not just a band of pale light across the sky. It is a vast spiral galaxy containing somewhere between 100 billion and 400 billion stars. The exact number is difficult to know because we are inside the galaxy, trying to understand its shape from within. It is a little like trying to map an entire forest while standing among the trees. Dust blocks some directions. Dim stars are hard to count. The centre is crowded and bright and difficult to see through. But even the lower estimate is almost impossible to hold in the mind. 100 billion stars, and our Sun is only one of them. Not the largest, not the brightest, not the oldest, not the most unusual. Just one ordinary star quietly burning in one spiral arm of an enormous galaxy, carrying Earth and the other planets with it through space. The Sun sits about 26,000 light-years from the centre of the Milky Way. That means that if light could travel from the galactic centre directly to us, it would take around 26,000 years to arrive. 26,000 years. When that light began its journey, human beings were still living in small groups, long before cities, long before writing, long before the first farms reshaped the land. The entire story of civilization, agriculture, villages, temples, roads, empires, books, machines, electricity, rockets, radio telescopes, all of it has unfolded during the time light could travel from the centre of our own galaxy to our region of space. That is not some distant galaxy. That is home. The Milky Way itself is roughly 100,000 light-years across. If you could somehow travel at the speed of a light, which anything with mass cannot do, it would still take 100,000 years to cross from one side to the other. That number's quiet but enormous. 100,000 years is longer than the entire span of recorded history many times over. It reaches back beyond the oldest cities, beyond written language, beyond the rise of agriculture, into a world where modern humans were still moving across continents and learning how to survive in changing climates. And light would need that long just to cross our galaxy. This is where the light year becomes more than a unit for nearby stars. It becomes the ruler for a whole cosmic structure. The same measure that helped us describe Proxima Centauri now stretches across spiral arms, star-forming clouds, dark dust lanes, clusters, and the crowded region around the galactic centre. The Milky Way is not a small island of stars. It is an immense city of suns. But unlike a city on Earth, its neighbourhoods are separated by distances so large that light itself becomes the only reasonable clock. Even the motion of our Sun around the galaxy works on a scale almost impossible to feel. The Sun orbits the centre of the Milky Way at a tremendous speed, roughly hundreds of kilometres every second. By human standards, that is almost unimaginable. At that speed, you could cross continents in minutes, and yet, the galaxy is so large that the Sun takes around 225 to 250 million years to complete one orbit, one galactic year. The last time the Sun was near this same place in its long path around the galaxy, dinosaurs were beginning to rise on Earth. Since then, they spread, dominated the planet, vanished, and mammals eventually filled the spaces they left behind. Human beings appeared only near the very end of that enormous orbit, so even motion becomes strange at galactic scale. Something can be moving incredibly fast and still seem almost still, because the distances are so vast. The Milky Way teaches us another kind of humility. We are not at the centre. Earth is not placed in some special glowing throne of creation. We live around an ordinary star in one region of one spiral arm, inside a galaxy so wide that our entire recorded history is only a brief flicker compared with the time light needs to cross it. And yet, there is something deeply beautiful about that, because we figured this out from here. From one small planet beneath one ordinary star, humans learned to measure the galaxy. We mapped stellar motions. We looked through dust with infrared light. We listened to radio waves. We used mathematics, telescopes, spacecraft, and patience to understand that the pale river of light across the night sky is actually our own galaxy seen from within. We're inside the thing we're trying to understand, and still somehow we can understand it. That is one of the quiet miracles of astronomy. The Milky Way is far too large to travel across, far too wide to see from the outside with our own eyes, and far too ancient to experience in full. But by measuring light, by noticing motion, by trusting the slow arrival of photons, we have learned our place inside it. A light year lets us speak about that place. It tells us that stars are not just scattered above us. They are arranged in a structure so vast that distance and time have to be spoken together. It tells us that our sun is one of hundreds of billions. It tells us that home is not only Earth, or even the solar system, but a great spiral of light turning slowly in the dark. And beyond this galaxy, the scale widens again. Light years stop being merely large. They become almost impossible to hold in the mind at all. Beyond the Milky Way, the word distance begins to change again. Inside our galaxy, a light year already feels enormous. It can measure the space between stars, the width of spiral arms, the long road from our sun to the galactic center. But once we look beyond the Milky Way, light years are no longer just a way to measure a galaxy. They become the language of the visible universe itself. The observable universe is the region of space from which light has had time to reach us since the beginning of the universe. That phrase sounds simple, but it carries a quiet limit inside it. We do not see all that exists. We see only what light has been able to deliver. The universe is about 13.8 billion years old, but the observable universe is not 13.8 billion light years across. It is much larger than that. Because while light was travelling toward us, space itself was expanding. The distance between galaxies was stretching. The fabric of the universe was growing while the light was still on its way. So today, the observable universe is roughly 93 billion light years across. 93 billion light years, that is not the distance to a star. It is not the width of a galaxy. It is the diameter of everything we can, in principle, observe from where we are. And within that vast observable region, there may be around 2 trillion galaxies, not stars. Galaxies, each one containing millions, billions, or even trillions of stars. Some are spirals like the Milky Way. Some are giant ellipticals glowing softly with older stars. Some are irregular and chaotic, shaped by collisions, gravity, and time. Each galaxy is its own island of light, separated from others by distances so large that even light needs millions or billions of years to cross between them. At this scale, the universe is not scattered randomly. Galaxies gather into groups. Groups gather into clusters. Clusters gather into superclusters. And across the largest scales, these structures form something like a cosmic web. Long, glowing filaments of galaxies stretching across darkness, with enormous empty regions between them called voids. These voids can be hundreds of millions of light years across, places so large and so empty that an entire galaxy could seem almost lonely inside them. And still, all of this belongs only to what we can observe. Beyond the edge of the observable universe there may be more space, perhaps much more, perhaps infinitely more, but we cannot see it, because its light has not reached us. It may never reach us, not because our telescopes are too weak, not because we have failed to build the right instrument, but because the universe has a horizon a cosmic horizon. There are regions so far away that light from them has not had enough time to cross the expanding space between there and here. And because expansion continues, some light being emitted now from very distant regions will never reach us at all. That is one of the most humbling ideas in cosmology. There are places in the universe that may be real, may contain galaxies, stars, planets, maybe even worlds with their own skies, but they are forever outside our view, not hidden behind dust, not waiting for better technology, causally unreachable. The universe does not allow every place to speak to every other place. This is where light years become more than distance. They become a boundary of knowledge, a way of saying not only how far away something is, but whether its light can ever become part of our sky. The cosmic horizon is not a wall you could touch. It is not an edge floating somewhere in space. It is an edge of information, a limit created by time, light speed, and the expansion of space itself, and that makes the observable universe feel both immense and strangely enclosed. We live inside a sphere of possible vision. Every telescope we build, every survey of distant galaxies, every image from deep space is looking outward through that sphere. We can see billions of years into the past. We can detect galaxies whose light began travelling before Earth had animals, before the sun looked quite the way it does now, before the Milky Way had finished becoming the galaxy we know. But even our deepest view is not everything. It is only everything that has reached us. That thought is quietly overwhelming. The observable universe is already too large for the mind to hold. 93 billion light-years across, filled with trillions of galaxies, shaped into filaments and voids, expanding as its ancient light travels through it, and yet it may still be only a portion of what exists. So the light year has carried us from a human step to the moon, to the sun, to the nearest star across the Milky Way, and finally toward the edge of what can ever be seen. And once distances become this vast, they change another old question completely. If the universe is so full of stars and worlds, why does it still seem so silent? The silence of the universe may not mean emptiness, it may mean distance. When we ask whether we are alone, we often imagine the question in simple terms. Are there other worlds? Are there other minds? Are there civilizations somewhere among the stars looking up from their own planets, wondering the same thing? But light years make that question much more difficult, because even if another civilization exists, even if it has cities, telescopes, mathematics, music, language, and radio signals, it may still be separated from us by a distance so large that communication becomes almost impossible in any ordinary sense. Take Proxima Centauri again. It is the nearest star beyond the Sun, only 4.24 light-years away. Only in cosmic language. If there was someone there, and we sent a message tonight, that message would take more than 4 years to arrive. If they answered immediately, their reply would take more than 4 years to return. A single exchange would take over 8 years. One question, one answer, nearly a decade. At 10 light years, the round trip becomes 20 years. At 100 light years, it becomes 200 years. You could send a message and never live to hear the response. Your grandchildren might receive the answer to a question you asked when you were young. This is not a failure of technology. It is the speed limit of the universe. Radio waves travel at the speed of light. So do the signals from spacecraft. So would any ordinary message sent across interstellar space. No matter how advanced the transmitter, no matter how carefully aimed the signal, information still has to cross the distance between stars. And those distances are measured in years of light. This changes the feeling of the Fermi paradox, the famous question of why the universe seems so quiet. Maybe the silence does not mean nobody is there. Maybe it means the galaxy is too wide for voices to easily find one another. Human radio signals have only been leaking into space for about a century. That means our earliest broadcasts have formed a bubble roughly 100 light-years in radius around Earth. That sounds large until you remember that the Milky Way is about 100,000 light-years across. Our signals have barely begun to cross the neighbourhood. On the scale of the galaxy, we have not shouted. We have whispered. And even that whisper fades as it travels. Radio signals spread outward, becoming weaker with distance, diluted across an expanding sphere of space. By the time ordinary human broadcasts reach even nearby stars, they are extremely faint, buried in the natural noise of the cosmos. A civilization would need to be listening in the right direction, at the right time, with the right instruments, on the right frequencies. And even then, what would they hear? Old signals, fragments from our past, a television broadcast, a radar pulse, a trace of technology from decades ago, arriving long after the moment that created it had passed. Now imagine a world around a star 40 light-years away, like the TRAPPIST-1 system. If intelligent beings there sent a message, it would take 40 years to reach us. If we answered, our reply would take 40 more years to reach them. An 80-year round trip for one simple exchange. That is not conversation the way humans understand it. It is correspondence across lifetimes. A civilization might rise, change, or fall between sending a message and receiving a reply. Governments could vanish. Languages could shift. The people who first listened may not be alive when the answer returns. Light years create isolation not by making life impossible, but by making connections slow. There could be many worlds, many oceans, many skies, many forms of life asking questions in their own ways. And still, each one might feel alone, wrapped in the quiet of its own star system, separated from others by years, centuries, or millennia of travel time. That thought is lonely, but it is also strangely precious. If we are alone, or effectively alone, then this small world matters. The voices here matter. The kindness here matters. The questions we ask beneath our night sky matter. Because even in a universe filled with stars, awareness may be rare enough, and distance may be wide enough, that every thinking world becomes something fragile and valuable. So what do we do with a universe this large? A universe where even light needs years, centuries, or billions of years to cross the dark. So now we can return to the word we began with. Light year. It sounds simple at first. A familiar phrase from astronomy. Something we hear whenever people talk about stars, galaxies, and the size of the universe. But now it carries more weight. A light year is not a year. It is a distance. The distance light travels in one full year, moving at about 300,000 kilometers every second, about 9.46 trillion kilometers, a number so large that it slips beyond ordinary imagination, yet precise enough for science to use as a ruler across the dark. We began with distances the body understands, a walk, a drive, a road across town. Then we moved outward, to the moon, where even our closest neighbour began to feel strangely far away. We followed the sunlight back across 150 million kilometres and noticed that even the sun does not reach us instantly. Then light itself became the guide. A light second, a light minute, a light hour, a light day, a light year. Each step carried us farther from the human scale, until the nearest star beyond the Sun, Proxima Centauri, became not a nearby point in the sky, but a distant island more than 4 years of light away. And once we understood that, the stars changed. They were no longer just bright dots scattered above us. They became old messages, Sirius from years ago, Vega from decades ago, Betelgeuse from centuries ago. The Milky Way became a galaxy measured not in miles or kilometers, but in tens of thousands of years of light. And beyond it, the observable universe opened into a horizon of galaxies, filaments, voids, and ancient light that has travelled for billions of years just to arrive here. That is what a light year really gives us. Not just distance, perspective. It reminds us that the universe is not built around the scale of the human body. It is wider than our roads, older than our histories, and quieter than our questions. It reminds us that even light, the fastest thing nature allows, still needs time to cross the dark. And yet, there is comfort in this, because even though we are small, we are not meaningless. We are small beings on a small planet, orbiting an ordinary star in one spiral arm of one galaxy. But we can look up and understand what we are seeing. We can measure the distance to stars. We can know that ancient photons are entering our eyes. We can realize that we are made of atoms forged in stars, looking back toward the stars. Light years speak of separation, but they also speak of connection. Every star you see has sent something across the darkness. Every point of light is a bridge between there and here, between then and now. And for a moment, when you look up, the universe becomes part of your own quiet night. If this calm journey through physics helped you relax, a gentle like or subscribe helps Physics by Night continue growing. And if you would like, leave a comment telling me where you're listening from tonight and what time it is there. Good night, and may the stars feel a little deeper now